Hi everyone, my name's Scarlet and I'm a student in the program on the environment at UW. I completed my capstone as a research intern at Friday Harbor Laboratories, and my project looked at how recreational boating potentially negatively affects eelgrass beds and how we can use data to better protect this valuable ecosystem. Firstly, I want to acknowledge that this Friday Harbor Laboratory project acknowledges the Coast Salish peoples of this land, the land that touches the shared waters of all tribes and bands within the following regions. So first, why eelgrass? Eelgrass Zostra marina is a critical species in the San Juan archipelago. It provides numerous ecosystem services, including shoreline stability, carbon sequestration, spawning and feeding grounds for marine life, and cultural significance for tribal nations. The populations in the San Juan Islands are declining. My project looked at 6 bays across the San Juan Islands that are both habitat for eelgrass and popular recreational boating destinations. The following bays are listed in Figure 1 with the red pins marking their locations. The decline of eelgrass in this region can be attributed to a variety of factors like warming oceans and disease, but recreational boating has also been identified as a potential threat. Boats damage eelgrass in two main ways: anchoring, which physically scours the seafloor, ripping eelgrass out by its roots, and shading, where a stationary boat blocks sunlight eelgrass needs to photosynthesize. Figure 2, right over here, represents an eelgrass bed that is being both scoured and shaded, emphasizing the negative impacts boats pose. Many previous studies have also shown that this damage tends to be concentrated in just a few heavily used spots within the bays. My research question was, how can we use automatic identification system, AIS, data to create a stressor metric that informs eelgrass protection policy? AIS is basically a vessel tracking system that broadcasts and monitors various characteristics of boats, including speed, location, and identity. This transceiver is primarily used for maritime safety to prevent collisions, but this data can also be repurposed to identify trends within boating behavior. Using this data, I worked with my co-intern to build a stressor metric, using 5 of these variables derived from AIS between 2018 and 2024 across these 6 sites. We ranked these variables based on potential impacts identified in literature, and using these variables, we found where high impact boating activity and eelgrass overlap across our survey locations. So now going into the results section, Figure 3 showcases the different variables we use from AIS, which include vessel class proportion, vessel width proportion, vessel density, mean daily anchoring events, and mean daily anchoring duration, all of which have a correlation to either shading or anchoring, and then how we define them within the metric. Our stressor score produced a high impact framework and allowed us to rank the 6 bays in terms of potential low stress to potential high stress. Figure 4 represents the final stressor scores across all 6 bays between 2018 and 2024, with higher scores representing higher potential stress. I'll give you a second to look at this graph because it's a lot of information to take in, but I'll also point out some significant points and data trends when the scores are interpreted visually. Firstly, there's a really notable spike between 2020 and 2021, which is right over here, which we think reflects the coding pandemic surge. After this peak, scores dropped again in 2022, but stayed higher than the 2018 and 2019 baselines, which suggests that boating pressure on eelgrass hasn't fully returned to pre-pandemic levels. In terms of individual bays, Shallow Bay, which is this light purple line right over here, stressor score doubled between 2019 and 2020. Blind Bay, which is the orange line, had the highest single score in 2021 at 73 out of 100. And Echo Bay, which is the green line, had the lowest stressor score in 2018, which was 17 out of 100. So kind of taking all this data, what does this actually mean for policy? So when comparing anchoring to mooring buoys, we see a difference of impact. Figure 5 represents a mooring buoy connected to the seafloor, presenting a more stationary impact, while anchors tend to drag on the seafloor, as shown in Figure 2. The placement of mooring buoys can be intentionally laid out in areas that avoid critical habitats. Therefore, an actionable finding of this project is around the design of mooring buoys. By mapping anchoring hotspots alongside existing buoy locations, we can identify a supply and demand formula that may offer more protection for eelgrass habitat. An example of this is in Figure 6, which is a shallow bay case study. Shallow bay is located on the upper right side of the San Juans. It's the left pin right over here. And this shows a comparison between anchoring events in 2018 and 2021, overlaid with buoy locations, which are the red dots, and the anchoring events are the blue dots, and optimal eelgrass zones. By visually understanding where supply and demand do not meet, this tool can give marine managers a spatially informed tool that they can use to make decisions about buoy placement in terms of eelgrass protection. So overall, this project shows how AIS, which is already being collected, can be repurposed into a really practical conservation tool. I would like to thank my co-intern Malene, my site supervisors, my faculty advisor, Bart Christian, Jeff Gakel, Claire Crawbuck, Jolene Boyd, and my friends and family who supported me along the way. Thank you so much.